You've probably seen a helicopter in a movie punch straight through a mountain range like it's nothing. Full power, nose down, climbing hard, no limits. But imagine you're strapped into a real helicopter somewhere over the Hindu Kush. The peaks below are sharp and gray, swallowed in cloud. The engine is screaming at full power. The rotors are spinning as hard as they physically can. And the helicopter stops climbing. Not because something broke, not because the engine failed. The instruments look completely normal. Power is good. Systems are green. Everything reads exactly the way it should. And yet the aircraft simply refuses to go any higher. The answer has nothing to do with mechanics, nothing to do with the engine, and nothing to do with pilot skill. It has everything to do with something you can't see, can't grab, and can't argue with. The AIR itself. And no amount of power changes that fact. Here's the thing most people get wrong about helicopters. They look at those spinning blades and see a giant fan. Something pushing air downward, brute force, like a ceiling fan on a summer day. That's not what's happening. Not even close. Every rotor blade on a helicopter is a wing, a shaped wing. It has a curved top surface and a flatter bottom surface, exactly like the wing on a commercial airplane. When the rotor spins, each blade slices through the air. Because of that curve, air moves faster over the top than the bottom. Faster air means lower pressure above. Higher pressure stays below. And that pressure difference is what pushes the helicopter upward. That's lift. That's the only thing keeping the machine in the sky. But here's the part that changes everything. That pressure difference depends entirely on air molecules. The blade has to physically push through them, redirect them, split them apart, and create that pressure gap between top and bottom. If there are fewer molecules to work with, the blade generates less lift. It's that simple and that brutal. At sea level, 1 cubic meter of air contains roughly 1.2 kilograms of molecules. Thick, dense, cooperative. At 10,000 feet, that same cubic meter holds around 0.9 kilograms. At 15,000 feet, it drops further. By 20,000 feet, you're working with less than 2/3 of what you started with. The rotor blades are still spinning. The engine is still burning fuel. Every system on board is doing exactly what it was designed to do. But the material those blades are gripping has become thinner, lighter, and less cooperative with every meter gained. Think of it like trying to row a boat across water that is slowly turning into mist. Your arms still work. The oars still move. But the substance you're pulling against is disappearing. Now the obvious question. If the air is getting thinner and the blades need more lift, why not just spin them faster? More speed means more air moved. More air moved means more lift. Problem solved, right? Here is where the engineering starts to fight back. Rotor blades have a hard speed limit, not a regulatory limit, a physical one. The tips of those blades are already moving at extraordinary speeds during normal flight, often approaching 700 to 750 kilometers per hour. That is already close to the edge. And here is why. As the rotor spins, each blade is moving fast in one direction, but the helicopter is also traveling forward. On one side of the rotor disc, the advancing blade is moving in the same direction as the aircraft, and its speed through the air adds up. On the other side, the retreating blade is moving against the direction of travel, and its effective speed drops. This asymmetry already creates problems. But if you push rotor speed higher to compensate for thin air, the advancing blade tip starts approaching the speed of sound. And at that point, something deeply unpleasant happens. The airflow around the tip goes transonic. Shock waves form along the blade surface. Drag doesn't just increase, it explodes. Vibration becomes violent and unpredictable. The blade stops generating clean lift and starts generating chaos. The aircraft doesn't fly better. It shakes itself apart. You cannot simply spin your way out of thin air. The physics of compressibility won't allow it. So the rotor is turning as fast as it safely can. The engine is producing full power. and the helicopter is running out of options. This is what aviation engineers call the service ceiling. Not the altitude where the helicopter stops flying, but the altitude where its rate of climb drops to roughly 100 feet per minute. That's about the speed of a slow elevator, technically still climbing, practically barely moving. Any turbulence, any temperature shift, any extra weight on board, and that last thin margin disappears entirely. The helicopter hasn't hit a wall, it's entered a shrinking corridor, and that corridor changes every single flight. Here's something most people never realize about that ceiling. It's not a fixed number printed in a manual somewhere. You can't look it up once and know it forever. It moves. Every single flight, the ceiling shifts depending on three things happening at the same time: weight, temperature, and pressure altitude. Together, these create what aviation calls density altitude. And density altitude is the real enemy. Start with temperature. On a cold morning, air molecules pack tighter together, more molecules per cubic meter, denser air, better grip for the rotor blades, better lift. The helicopter performs closer to its published numbers. Everything feels solid. Now take that same helicopter, same location, same elevation, and wait until a hot afternoon. The air expands, molecules spread apart, the density drops, and the effective altitude of the helicopter's environment rises even though the aircraft hasn't moved an inch. A helicopter sitting on a runway at 8,000 feet on a warm day might already be performing as if it were at 10,000 or 11,000 feet before it even lifts off. It hasn't climbed. The atmosphere around it has simply become less willing to cooperate. That's density altitude. The ground says one number, the air says another, and the AIR always wins. Pilots operating in mountainous regions plan around this obsessively. They do not just check the weather before a flight. They calculate density altitude down to the specific hour of the day. They know that a mission perfectly achievable at dawn, when the air is cold and dense and cooperative, may become physically impossible by noon when the same valley has baked in the sun for 5 hours. The physics of the atmosphere do not negotiate. They do not care about the mission, the schedule, or the urgency. They simply present a number, and the helicopter either operates within that number or it does not fly. This is not some theoretical edge case that only matters in textbooks. This is the daily operational reality for every helicopter crew working at altitude. And the consequences of getting it wrong are genuinely staggering. During military operations in Afghanistan, helicopter crews faced this reality on almost every mission. The mountains there regularly exceed 10,000 feet. The valleys where troops needed extraction, where wounded soldiers waited, where supply drops had to land, those valleys sat at altitudes where heavy helicopters were already brushing against their performance limits before the mission even began. The air was thin, the terrain was unforgiving, and the margin for error was almost non-existent. The solution was often brutal in its simplicity. Remove weight, leave cargo behind, reduce the number of passengers, strip out anything that is not absolutely essential. Sometimes fly 2 shorter trips instead of 1, sometimes 3. Not because the helicopter was broken, not because the crew lacked skill, because the air at that altitude simply could not support the load. Take the CH-47 Chinook, one of the most powerful cargo helicopters ever built. Twin rotors, massive lift capacity, designed to haul vehicles and artillery and dozens of soldiers at once. At sea level, it's a workhorse that can carry extraordinary loads without hesitation. Put that same aircraft in the Afghan mountains at 10,000 feet on a warm afternoon, and the picture changes completely. That same Chinook might carry less than half its rated capacity. Not because the engines were failing, not because something was damaged. The engines were running perfectly. Every system was green. The aircraft was doing exactly what it was designed to do. But the atmosphere had changed the rules. The air was thinner, The density altitude was higher, and the physics simply would not allow the full load off the ground. Every kilogram above the performance limit is a kilogram that the atmosphere will not lift. The engine can produce all the power it wants. The rotors can spin at their maximum safe speed. None of that matters if the air molecules are not there to generate the pressure difference the blades need. The engine cannot negotiate with the atmosphere. It cannot argue. It cannot push harder and win. The air gives what it gives, and the helicopter works within that allowance, or it stays on the ground. But the weight problem is only part of what happens when a helicopter pushes into thinner air. There is something the pilot feels directly through the controls that most people never hear about. At altitude, the rotor disc itself becomes uneven. On the advancing side, the blade is moving quickly through the air and generating relatively normal lift. On the retreating side, the blade is moving more slowly relative to the airflow. In thin air, that slower blade loses lift significantly. The result is an asymmetry. One side of the rotor is working harder than the other. This creates a rolling tendency that the pilot must constantly correct, not once, not occasionally, but every single second. At low altitude in dense air, these corrections are small and immediate. The controls respond precisely. The aircraft feels solid and connected. You move the stick, the helicopter moves. Cause and effect, tight and responsive. At 15,000 feet, the picture changes. The controls feel looser. Inputs take longer to translate into actual movement. The aircraft feels like it is floating rather than flying, and not in a comfortable way. Small turbulence causes larger deviations. Corrections overshoot. The pilot is no longer commanding a responsive machine. They are negotiating with one unexpected gust, one passenger shifting weight in the back, 1 degree rise in outside temperature. Any of these can push the aircraft from marginal performance into no performance at all. There is a moment in high-altitude helicopter flight that experienced pilots describe with remarkable consistency. A moment when the aircraft simply stops responding to climb input. You pull more power. The engine responds, the rotor spins, and the helicopter stays exactly where it is, vibrating, holding, going absolutely nowhere. You have reached the top of what the atmosphere will allow. The most extreme example of this boundary being tested is the 2005 Everest landing by Didier Del Salle. An Airbus Écureuil was sitting on the summit at 8,848 meters. Air density was roughly 30% of sea level. The rotor was operating in conditions so marginal that a fully loaded aircraft attempting the same feat would not have left the ground. The physics simply would not permit it. This is the reality of helicopter performance that never appears in the dramatic footage. You see the mountain rescue. You see the combat insertion. You see the aircraft arriving against an impossible backdrop, and it looks effortless. It looks like raw power conquering nature. But what you do not see is everything that made that moment possible. The hours of planning that preceded it, the weight that was stripped out of the cabin, the timing chosen specifically to match the coolest, densest air of the day. The fuel load calculated to the kilogram, not a drop more than necessary, because every extra liter is weight the atmosphere might not support. High-altitude helicopter operations are not just physically demanding. They are a constant negotiation between pilots, engineers, and an atmosphere that grows less cooperative with every foot of elevation gained. The helicopter does not have a fixed performance limit stamped on a spec sheet somewhere. It has a shifting one, a boundary that moves with temperature, with weight, with moisture in the air, with the time of day. Pilots do not fly to a ceiling. They fly toward a performance budget that is always being spent. And every mission is a calculation of how much budget the atmosphere is willing to give. So here's where you land. That helicopter over the mountains, engine at full power, rotors at maximum speed, Every system reading perfectly normal, going absolutely nowhere. You used to look at that and think, something must be broken. Now you know what's actually happening. A shaped wing fighting for pressure difference in AIR that's slowly disappearing. A blade tip approaching the speed of sound with nowhere left to go. A ceiling that shifts with temperature, weight, and time of day. A performance budget that the atmosphere sets and no engine on Earth can override. The machine isn't failing. The AIR is simply dictating terms. And here's what makes this even more interesting. Fixed-wing aircraft escape this exact same trap. They trade one dimension for another, using forward speed to cheat the very physics that eventually stops every helicopter in its tracks. How they do it is a story worth understanding on its own. Subscribe so you don't miss it.